Good morning. This is an implementation video on the titration of a metal, which we will call M, with EDTA, which we are going to call Y. And this is a general approach toward calculating the titration curve, which means we don't need to make any assumptions. We're going to use the quadratic equation to calculate the metal concentration at any mixture of metal and EDTA. So to begin, remember that EDTA is a polyprotic acid, and it will, in the fully protonated state, have 6 protons. In the fully dissociated state, it will lose 6 protons, and we model EDTA speciation by assuming that the EDTA in the fully dissociated form binds to the metal. And that's actually a pretty good assumption. So we need to calculate the pH side reaction coefficients, the pH dependent side reaction coefficients, before we can start. And so we've already done that in class. We already have an equation for calculating the fraction of each species in a hexaprotic acid system. But just to remind you, I have the pKs, pK1 through pK6. So these are the pK1 through 6 for EDTA. If I know the pKs, I can take 10 to the negative log, 10 to the negative pK to get the K. And then this problem requires us to define the pH. So typically the pH is buffered in all of these problems. And so we're going to be buffered to pH 7. We know the pH, we know the H plus. If we know the H plus and the Ks, we know the denominator for this hexaprotic acid system. So this should look pretty familiar. H plus to the 6th, K1H plus to the 5th, all the way out to K1, K2, K3, K4, K5, K6. That's the denominator. This is why we use Excel, because you'd never want to have to calculate that by hand. So if we know the denominator in our polyprotic acid system, the numerator in this case, and the species we're interested in is the fully dissociated form, so that's K1, K2, K3, K4, K5, K6, divided by the denominator. All right, so what's that say? It says that the fraction of EDTA that's dissociated, fully dissociated at pH 7 is 3.7 times 10 to the minus 4, or something on the order of 0.03%. So that seems like a very small fraction, but remember, we're going to multiply that by the equilibrium constant for EDTA, and those equilibrium constants are big. So even though only a small fraction of the EDTA is available to bind metal, that binding constant is big. As soon as it binds, you no longer have any EDTA in the fully dissociated form. The equilibrium is going to shift, and you will continue to provide plenty of free EDTA to bind metal. So the next thing we need to know is what's the KF, or the log K, and I'm going to call it a KF or log K formation for the metal of interest. And if I pick copper 2 as my metal of interest, its binding constant is 18.35. Its log binding constant is 18.35. That's big. So now KF is just simply the anti-log of that, right? 2.2 times 10 to the 18. Now what's important is that we calculate the KF prime, and the KF prime is the conditional constant. So you notice what I've done is I've taken KF, I've multiplied it by alpha, and I have this other term M39, which I will get rid of. That was a carryover from a previous application of this spreadsheet. So KF prime is simply the K times the fraction of EDTA that's available for binding, and you'll notice that, there we go, KF is smaller, KF prime is smaller than KF by the alpha, but it's still really big, which is why EDTA is an effective Lewis base to bind metals. Now, often when you do the algebra, it's convenient to have the reciprocal of KF, and some folks refer to that as the KD, and I've got that same M39. I'm going to get rid of that. And so there's my KD prime, and the KD prime is simply nothing other than the reciprocal of KF prime. Okay, so that defines the chemistry. Now to define the titration. We are going to be titrating a metal with EDTA. So when you do it, so the metal is in the beaker. And so we need to tell the calculation how much stuff is in the beaker. And I pick 50 mils. So we can change this number 50 mils, but I pick 50 mils. So that's the amount of metal in the beaker. I also need to tell it what's the concentration of metal. Now this is total metal, so it includes metal in all of its forms. And so I made up a 0.01 molar solution of copper. Maybe I used copper nitrate. That's a common counterion for copper. So that's 0.01 molar copper. Now the EDTA concentration, that is the concentration that would be in a burette if you were doing a titration, or in a pump if you were pumping it in, or you could just be pouring it into the solution. But it is the concentration of our titrant in any form in which we introduce it into the problem. Now we know these are a one-to-one stoichiometry, metal and EDTA. So notice those two concentrations are about equal. Well, they're not about, they are equal. And since a one-to-one stoichiometry, we expect the equivalence volume, the point at which the EDTA binds all the metal, to be 50 mils. If I made the EDTA concentration twice as high, you'd expect the equivalence volume to be 25 mils. We'll test that assumption after we finish working through the implementation. All right, that's all the starting material that we need. Now into a little bit into the theory. We're going to solve this problem analytically. So we're going to solve for the metal concentration. We could actually solve for any of the components of the system. We could solve for free EDTA. We could solve for bound metal EDTA. We could solve for metal. I chose to solve for metal. And so I'm going to do this by solving this equilibrium expression, and I need a couple of additional terms. So there's 3 unknowns in this, and I've got 2 additional knowns, and these are the mass balances for EDTA and metal. So Ty, which is my abbreviation for total EDTA, is the sum of the unbound EDTA and the metal bound EDTA. It can be in one of 2 forms. Add them together, that equals the total. Total metal, and I should clean that up a little. Let's just make that Tm. There we go. Tm, get rid of the space, is the metal plus the metal EDTA. Again, it can be in one of 2 forms, and you simply add them up. My equilibrium expression is products over reactants. Notice I've written this as a formation, and notice I've written it as Kf prime. We're going to use the conditional pH-dependent equilibrium constant. All right, so now we'll go ahead and we're going to do a little algebra. The approach I'm going to take is I'm going to solve the equilibrium expression for the metal. And to solve it for the metal, it would be really helpful if I had an estimate or a value for my and a value for y, and then you know Kf prime, so you can solve for metal. All right, so now let's go get an estimate for my. Reorganizing the second equation, I get my equals total metal minus the metal. Notice it's a function of metal, and this is going to be my algebraic approach. I'm going to try to get everything into this Kf expression, either a known or metal, and then you can just simply solve for metal. So there's my my is Tm minus metal. I can also reorganize the top equation for y, and y is Ty minus my. Well, I have an expression for my, so I plug that into here, and now I get y equals Ty minus T metal plus m. Okay, so I think I did my algebra correctly here, and now I can plug this y in here, I can plug this my in here, and I have a messy quadratic, and I solve the quadratic, or I reorganize the expression to be ax squared plus bx plus c, and I now have computed those a, b, and c terms below, and here they are. Well, it turns out that the a term in this quadratic expression is 1, so notice the whole column e is set to 1. The b term is equal to 1 over kf, which is also kd, so there's b17, minus B23, total metal. We're going to come back and define those in a second, plus C23, total EDTA. That's my B term. Now my C term is 1 over, it's just KD, or 1 over KF, negative 1 over KF, times B17, which is total metal. Okay, so that's my A in the AX squared, B in the BX, and C, the intercept, in my quadratic equation. Okay, if I know my A, B, and C, I can plug them into the quadratic equation, and notice I get negative B plus the square root of B squared minus 4AC all over TA, and I don't need that M39, and there it goes away. There, I fixed it all the way down. So that gives me my metal concentration, and guess what? If I add 0 EDTA to a solution of 0.01 metal, I better get 0.01 metal, right? If I start with 0.01 molar metal and I don't do anything, I'm at 0.01 molar metal. That is a fairly straightforward calculation. Of course, it will get more complicated as we add EDTA moving down. And then P metal, like pH, it's often convenient to take the negative log of a species that's going to change over several orders of magnitude, and that's exactly what I've done. I've taken the negative log of the metal concentration to plot, or to calculate and then plot P metal. So the last thing I need to do in this implementation is to tell you about these T metal and T EDTA terms. So let's start with T metal. I started with a 0.01 molar solution. Now what will happen is I add titrant is I will actually dilute this just a little bit. Well, if I double the volume, I guess I dilute it by half. So to correct for the dilution, I recognize that the concentration of metal is equal to the moles of metal I dump in the beaker divided by the total volume of liquid that's in the beaker. So let's see how I implement that. The numerator is the total moles, so it is going to be equal to B18 times B19. The initial volume times the initial concentration gets me the total moles. And what's the volume? Well, the volume is going to be my initial volume, which is 50 mils, plus any volume I added as a function of as a titrant. So as I increase the titrant volume, I effectively dilute the total metal concentration, and you can see that it goes from 0.01 to 0.0098, boom, 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 all you go down here. By 21 mils, we've diluted it by about 30%. So that dilution factor is real, right? It can be quite significant. So you can't ignore the dilution of your analyte by your titrant. All right, so you can think about that. We're diluting what we're titrating with the titrant that's going in. All right, well, the total concentration of EDTA follows exactly the same approach. The numerator is the total moles. So now that's going to be the concentration of EDTA times its volume. Well, if you don't add any, the first step is 0, but it's going to have a real concentration at every other titrant volume. So it's concentration times volume gets me moles, and then do the exact same thing, divide by the total volume in the system. So it's the initial volume plus the titrant volume. And now we're done. So I now have estimates for total metal moving forward in a titration scheme. I have a concentration of total EDTA moving forward. I have my A term, my B term, my C term. That allows me to calculate metal. That allows me to calculate P metal. And now I come over to my graph. You notice the y-axis here is P metal. The titrant volume is on the X. So if you add 0 EDTA, you should end up with a P metal of 2. Because its concentration was 0.01, and therefore the negative log of 0.01 is 2. And notice that the total metal concentration definitely, the P metal increases, which means the concentration decreases, but it doesn't decrease that much over this region until we get to 50 mils. Remember, we said that the equivalence volume in this problem was 50 mils. Then you get a very dramatic change in the metal concentration as the EDTA reaches a stoichiometric point and begins to complex all the metal. And then after that, you now have excess EDTA, and your metal concentrations are now quite small. So in class, we did a calculation here, we did a calculation out here, we did a calculation in the middle, and this implementation allows you to do it anywhere along the curve. So now let's go ahead and change the problem a little bit. Let's change the volume from 50 to 25. If we put in half as much metal, I'm right here, boom, it goes to here. Put in half as much metal, you need half as much EDTA. Okay, that sort of makes sense. We'll put it back to 50. All right, what happens if I decrease the metal concentration by half? So I'll make it 0.005. Okay, now I put in half as much metal, kept the volume the same. All right, half as much metal and concentration. Again, the equivalence volume changes to 25 mils. Notice that this point right here is the same at halfway point, is independent of the concentration of the initial metal and the volume. It is the stoichiometric point, and it turns out to be effectively very close to the square root of the KD. Now we've got point before the equivalence, we got the point after the equivalence, and we've got the metal concentration at the equivalence. So that's helpful. Now we can do some other things. Let's imagine we're doing this titration not at pH 7, but at pH 9. I'll put in 9. My alpha now becomes quite a bit larger. We now have this part of the titration curve, the pre-equivalence volume, looks identical. But what's changed is the after equivalence, and that's because our EDTA has effectively become a better ligand, and now our free metal concentration is down on the order of 10 to the minus 16, or P metal is 16. All right, so you change the pH, you change this curve. We were at 7, we went to 9. Let's go from 7 and we'll go down to 4. So now we're going to make EDTA a weaker complexant because it's going to be in competition with all those protons. And boom, notice it went from 10 to the 16 down to something like 10 to the minus 16 down to 10 to the minus 9, or a P metal of 9. EDTA still binds copper pretty well, even at pH 4, but it doesn't bind it as well as it did at 7 and 9. And of course, if you go to 2, we expect this process to even go at 2. Boy, there's even hardly any indication of a break. So at pH 2, the protons are more effective at binding EDTA than copper. Let's go back to 7. And now we can play around with different metals. So copper is a pretty good Lewis acid. It likes to bind to likes. It's like we gave copper personality. The copper has a high affinity for EDTA, but other metals have a much lower affinity, species like sodium and potassium and even calcium and magnesium. And so we can put in a log EDTA of 4, which is pretty typical of group 1 metals. And you'll notice it with a log K of 4 and a pH of 7, EDTA has essentially no reactivity. So group 1 metals are seldom complex by EDTA, and in fact, we often make up our solutions of EDTA as the sodium salt, and that's because the sodium doesn't play a significant role in EDTA binding. So we get tetrasodium EDTA as our analytical reagent, and we dissolve that up to make our EDTA solutions. So Again, we can play with these Ks. You could make it big. Iron has a log K of like 25. Boom, it blew up my spreadsheet. You can see right here, it doesn't work. It's not that my math is wrong, it's just Excel can't handle it. And that's because these numbers way down here are getting too big. This thing's getting crazy. So we'll just make the pH a little lower. There we go. And so I get my curve. So if you make the log K too big, you got to play a couple of more tricks algebraically in order for Excel to be able to calculate the quadratic effectively. Welcome to the real world here. All right, so I hope this helps. In review, we started with the pKa's and the pH to get our alpha. Once we knew the alpha, we could calculate the conditional formation constant. Once we knew the conditional formation constant, we could get the conditional dissociation constant. They're reciprocals of each other. We recognize that if we know the volume and the concentration of the metal we put in, we know the metal concentration, and we can correct the metal concentration for dilution moving forward. If we know the EDTA concentration and the volume you put in, we can calculate the EDTA total concentration. We also correct that for dilution. Knowing total metal and total EDTA, we can use simple mass balances in the equilibria to solve for the metal. We do that by solving the quadratic in terms of the A, B, and C terms. That gives me the metal concentration, and from the metal, I get the P metal. I hope this is helpful. Have a great day.